Hey, welcome back. Today we're going to take a little bit closer of a look at some differential equations. We're going to continue exploring differential equations and modeling with differential equations. Specifically, we'll be talking about exponential growth and decay models. In this one, we're just looking at exponential growth. We're just going to focus our attention on populations. So we're going to talk about an exponential growth model and also talk a little about a logistic growth model and kind of compare the two. So let's dive into it. Especially now that we have the tools that we need to solve some of these differential equations, if we can do the separation of variables technique. So remember from a while back that the rate of growth of a population, which we can describe as the derivative dp dt, is proportional to the size of the population p. So for example, when the population is small, the growth of the population will also be small, the growth rate that is. When the population is large, the rate of growth of the population will be large. So we kind of have this, proportional relationship with the size of a population and the rate at which that population grows. So we can describe that as a differential equation. We've seen that before, dp dt equals kp, where k is kind of just some constant, how those two are related, and we can kind of find different ways to find those. So now that we know the separation of variables technique, let's go ahead and actually use that to solve this differential equation. Now this is not a new differential equation. We've seen it before. And in fact, a few sections back, we looked at a solution to this differential equation. It was kind of just presented to us and we verified that it was in fact a solution. But now we're actually going to go ahead and find the solution ourselves. So I have this as an exercise for you to go ahead and try, since we know that separation of variables technique. So go ahead and pause the video when you're ready and solve this differential equation. And remember, to do that, you want to get basically all the p's on one side. I'd recommend the left side in this case, and then all the other t's on the right side of the equation, and then integrate, right, to solve. So go ahead and pause and come back when you're ready. All right, welcome back. So let's go ahead and give this a try. Hopefully you've got a good amount of stuff on your paper here, and we'll see if it kind of matches up with what I'm about to go through. So we have our initial, right, differential equation, Kp, there we go. I know I'm gonna need a decent space here, so I'm gonna shift that up. All right, so we wanna solve this differential equation. So we're gonna go ahead and do the dt to the other side. And we want to get the p's together, so we're going to go ahead and divide both sides by p. But I'm going to actually think of that as 1 over p instead, just to make the integration a little bit easier. Here we go. We have basically everything together. Now, let me just point out with this k is a constant. So, you could keep this on the right side with the t, or you could put it on the left side with the p. I would prefer it to be a constant multiple instead of like a fraction. So I'm going to go ahead and keep the k over with the t. But if you did something different, that's probably okay. All right, so we're going to go ahead and integrate both sides here. Integrating the left side gives us the natural log of the absolute value of p. We'd probably assume that the population is positive anyway, wouldn't we? And then the antiderivative of k with respect to t would be kt plus some constant, right? I'm going to go ahead and call this c sub 1 because I might want to use a regular c in a little bit here. So we'll say natural log of absolute value p is kt plus some arbitrary constant. If you chose something different than c sub 1, totally fine. So we'd like to go ahead and solve this for p. To do so, we'll think about e to both sides essentially, right? So we get p on the left side, e to the kt plus some arbitrary constant. But we can kind of rewrite this a little bit. I'll come over here. And what we would have then is, if you think about rewriting this, you can think of it as multiplying by e to the c sub 1. So I'm just going to say, let's let e to the c sub 1 be c, some other arbitrary constant, right? So I can write this then as c e to the kt. Now this is an initial value problem. We have that p of 0 equals p sub 0. So we're kind of just, using a general initial population here for that. And we will go ahead and interpret that. Maybe I gave away the interpretation a little early. It's okay. We have kind of seen this already. So let's go ahead and solve this initial value problem. I would do p of 0, c e to the k 0. So that equals c, doesn't it? Because I'd have e to the 0, which is 1. And we know that p of 0 is p naught. So I get that c is p naught. That arbitrary constant c represents the initial population for this particular population model here. So p of t equals p sub 0 or P naught e to the k t. So we just use the separation of variables technique to solve this general differential equation, dp dt equals kp, and we have what's called an exponential population model, or sometimes exponential growth model, but specific to population. So the solution is p of t equals p naught e to the kt. Now let's talk a little bit more about this particular model. I'd say it's relatively clear that p sub 0 or p naught is the initial population, right? You plug in 0 for t, this becomes 1, so you end up getting that initial population value, okay? The constant k is a little bit more elusive, like we have to kind of really think about what that k value will tell us, but it does have a very important interpretation on like a particular population. So if we think about solving this, this differential equation for k rather than p, we would just divide both sides by p, right? We'd have divide by p, divide by p. So we get that k is dp dt divided by p. So you can think of k as really being like the ratio of the rate of change of the population, that's dp dt, and the population itself, p, right? It's the ratio of those two things. So it's essentially like the contribution to the rate of change from like one single person, like one single p for population, like how much rate of change they're going to contribute to that population essentially. So we can call k, we call it the relative growth rate, or sometimes the per capita growth rate. So let's go ahead and look at a specific example so we can kind of wrap our head around this k value idea. So we're going to look at the Earth's population. In recent years, now this table shows us the Earth's population for various years in billions of people. Okay, so you can kind of see, the population increasing here. And I think this data is just fascinating. So I'm excited for us to dive into this and look at this in a kind of differential equations lens. So first thing we're going to do is we're going to try to represent this data with that exponential population model or exponential growth model, and then kind of make some predictions. Think about whether some of those predictions make sense or not, and then maybe think about if there could be a better way to model this particular data or population data in general. Okay, so let's start from the beginning. I'm going to actually go ahead and read this whole thing. The table below shows some data for the Earth's population in recent years in billions of people. Let P of t be the population of the Earth in billions of people, t years after 2000. Okay, so I'm going to add a few things here. This is going to be P of t, right, in billions here. And then we are going to just happen to set this at t years after 2000. It just kind of makes things easier to have some sort of starting point and to use like 0, 1, 2, 3 instead of like 2000, 2005, that kind of thing. So that means this is going to be 0. I'm going to put t here. This would be 0, the year 2000. 2001 would be 1, right? Just go ahead and write this in above your table. Notice this little skip here from 2002 to 2005, and then 7, and then 8, 9, 10. Okay, and then this would actually be negative 1. It might seem kind of strange to have negative time, but based on, making 2000 t equals 0, we would have negative numbers that would correspond to years before the year 2000. Okay, so let's jump into part A here. Use the data from the years 2000 and 2001 to estimate the relative growth rate k using the population growth equation that we just came up with. And we're going to try to keep k exact instead of rounding it, and then we'll use it to model the population of the Earth. That is usually the case. You do kind of want to try to keep k as an exact value so that your model can be as accurate as possible. Okay, and then we're going to use it to answer a bunch of questions, but let's go ahead and dive in with the first part here. So we're going to use the data from 2000 and 2001. So I see that P of 0, right, that would be the year 2000. That is 6.084. And that is the initial population. I'm just going to go ahead and write that in here. That's P sub 0. We'll use that in our exponential growth model. And then P of 1 is, I can see from the table here, 6.159. 6.159. And remember, those are in billions of people, right? Okay, so what we're going to try to do is try to make a specific model for this particular data set. And we just happen to choose 2000 and 2001. You'll see later if we make different choices, we might have different k values, which is actually really interesting to think about. But we'll get there. Okay, so here we go. We're going to go ahead and try to find this k value. And there are multiple ways to do this, but this is the way that the book that we're using right now approaches it. And so I'm going to try to be consistent with that, but I will show you another way in a moment. So we know that P of t is the initial population, which was that 6.084, e to the kt. right? So what we're going to do is we're going to use this other data point that was in the year 2001 to find that particular K value. So P of 1, plugging in 1 here, I get 6.084 e to the K times 1. So that would be e to the K, right? And I know that that result should be 6.159. So what we have essentially is this exponential equation to solve, which you've done before. It might be a little rusty, that's okay. So you want to isolate the exponential part, and then we'll use logarithms. So let's go ahead and divide by this initial population. We'll have 6.159 divided by 6.084. That equals e to the K. So then K is equal to the natural log of that value, that 6.159 divided by 6.084. Now, I do kind of like to wrap my head around this K value, so I do tend to find a decimal approximation for it, which we're going to go ahead and do right now. So it was the natural log of 6.084 divided by, I don't remember, oh, sorry, 6.084 was in the denominator. 6.084, and then the numerator was that 6.159. Here we go. So I get a K value of about 0.01225. And you could go out further, 205, whatever. I just like to get an idea of roughly what the value is. But we are going to actually keep it in this form for our calculations, just to make sure that we, have as accurate of a model as possible. If I round it only to like 2 decimal places, I lose accuracy. 3, better, but still lose accuracy. So let's just not do any rounding. We'll keep it exact. Okay, let me get rid of that line there. So this means that the exponential growth model for the Earth's population is going to be that 6.084 e to the, now again, I'm going to keep this exact, natural log of 6.159 divided by 6.084 t. Now, if you want to, you can just leave this as a K, and you have told the reader what K is. So if you get tired of writing this kind of same long expression over and over again, feel free to use variables to replace that. Write variables that represent constants. So in this case, just K. So it'd be fine if you just wanted to leave a K there. But don't do the rounding though, because again, that loses out on accuracy a bit. And another way you could write this model if you wanted to, I just want to show you a way you could simplify this if you so chose to. Right, e to the natural log of something is the something itself, right? Those things undo one another. So this can also be written as that 6.159 divided by 6.084, all raised to the t. That's just another way that you could represent this population model. But I'm going to go ahead and leave it in its exponential form, just because it's, that's kind of the general form that we have. So okay, so we've done that part A here, and now what we're going to do is we're going to answer these 4 questions. First off is, what does the exponential model predict will be the population of the Earth in the year 2010? And we can actually have that data, so we'll be able to compare and see how this model did, see how accurate it is. Okay, so here we go. We're going to do P of 10. Actually, this is not B, this is part 1. So P of 10, and I'm going to go ahead and use Desmos rather, to do this. I think I'll just do this so I can see it a little bit better. So first thing I want to do is actually type in our model, and then I can just type in P of 10 later. So P of t equals 6.084 e to the natural log 6.159 divided by 6.084 t. Now another option, since we already did type that in here, is you could say K equals that, and then rather than having to type this whole thing in again, you could actually just go ahead and make that a K. So lots of different options. You do what feels best to you. And I'm going to kind of change this a little just so I can see that exponential growth really nicely there. Okay, so again, you could have left this, oops, it's changing my thing. You could actually have this natural log of that quotient typed in there. That would be fine too. But the less things you have to type, it's kind of nice. So P of 10, that's what we wanted to put in. P of 10 is, I'm going to go ahead and do a split screen here. P of 10 is about 6.877. So remember what that means. That means billions of people in the year 2010. And let's see how accurate that is with the data that we have. Okay, so we're going to go back up. So keep that in mind, 6.877 billion and we had 6.831. I feel like that's pretty good. I'll just put that in parentheses, pretty good. We could calculate an error if we wanted to, but it's relatively close. I'm relatively happy with that. Okay, is this close to the actual population in the table? Yeah, pretty close. Okay, part 2. When does the exponential model predict the population will reach 10 billion? Now I'm going to show you a few different ways that you can do this particular one. Okay, I'm going to go ahead and do it up here. So this is part 2. So let's actually solve it by hand, because I think that that's one important way to know how to solve these types of problems. And I'll also show you how to do it using technology, like using Desmos or GeoGebra. We'll use GeoGebra a little bit later on. So we'll get a good variety of technology and some stuff by hand. So we want to know when the exponential model will reach, or will predict, a population of 10 billion. So we want to know when that 6.084 e to the natural log. Again, you can just use a k here if you'd like. So that was 6.159, 6.084 t. When will that equal 10? Right? We're going to try to solve for t. So we will divide both sides by that 6.084. Divided by 6.084. Now we'll take the natural log of both sides, which will isolate this exponential piece, which also has a logarithm in it, doesn't it? And again, if you want this to be a k instead, that would be fine. So then we will solve, oh wait, I'm sorry, I forgot to write my natural log in there, didn't I? Let me recap for a moment. We took the natural log of both sides in that particular step, which isolated the exponential piece here, and then we'd have the natural log of that right side of the equation over here. So now to solve for t, we will divide both sides by that value. So I'll have the natural log of 10 divided by 6.084. And then divide that by that whole k value, 6.159. divided by 6.084. So again, if you want that to be written as a k, that would be fine. All right, let's go ahead and put that into Desmos. Ooh, I'm going to have to switch these around, I think, because I have a second monitor plugged in, so it took me all the way up to the top, didn't it? Okay, so we'd have that natural log 10 divided by 6.084. And you could, again, type k in here. That's fine. I'll show you both. Copy, paste. If you didn't have the k defined in here, you just type that whole thing in. And notice you get the same thing, right? I just wanted to show you that. So in solving that for t, we get 40.558 roughly. And remember, that's how many years after after the year 2000. So about 2040 to 2041. I'll just put it like a range, so that's fine. You could get more specific if you wanted, like July of 2040, but this is all just predictions that we're kind of making here. So roughly the year 2040 is when this exponential model predicts the population to be 10 billion. Okay, let's keep going with this. 3, here we go. All right, it says, oh, I was going to show you how to do this with technology too, wasn't I? Let me pop back over to Desmos here. So another way we could do this is actually type in y equals 10 and then see where these intersect, right? This is our population curve. This is 10 billion. So you can see the intersection of these as well. And I'll actually go ahead and type this in, 40.558. And notice that's the same as, so there's that intersection point. That's the same as what we found here as well. It gave it to us accurate to 3 decimal places. If you wanted more, you'd want to actually maybe solve it by hand so you can get more. Or use GeoGebra. We'll use GeoGebra later, so I'm not going to do it right now. Okay, so that's another way that we could do it. Okay, so now what we're going to do is use the exponential model to estimate the population of the Earth in the year 1975. So the year 1975 would have a negative t value, right? Because it comes before the year 2000. So we would be finding p of negative 25. Because 1975 is 25 years before the year 2000. So let's see what that predicts. P of negative 25. And I get about 4.479. About 4.479 billion people. Now that's not in our table, is it? And so what we'll do is we can just kind of hop over to Google or whatever your preferred search engine is, and we will figure out what the population was in the year of Earth. And notice I typed it in already because I was checking earlier. 1975. So it says 4.063 billion. So 4.063 billion is the actual. And that's pretty close. It's not going to be perfect, right? We're just modeling here. Pretty close. Okay. All right. Next thing is what does the exponential model predict for the population in the year 2500? Seems like a long way away, doesn't it? So the year 2500 would be t equals 500 because 500 years after 2000. So p of 500, let's see. I'm going to pop back over to Desmos here. P of 500, wowza, 2,784, 2,784.124 with rounding to 3 decimal places. So let's think about how big that is. That's in billions, right? Okay, so that means that that would be 2,784,124,000,000, like that. That is a lot of people. So the second part of that question was, does this seem reasonable? Why or why not? So no, this does not seem reasonable, right? This is not reasonable for the population of the Earth. The Earth would not be able to actually sustain this many people. I'll just write not sustainable. So it's pretty unrealistic. So we kind of want to take this exponential model with a grain of salt. And let's look at, so now we're going to go ahead and graph the data along with the solution curve that we found, that basically the exponential growth model, and kind of see what happens and what goes on as time increases to large numbers. So let's put the data in. I'm going to scroll back up here. Now in Desmos and GeoGebra, you can do a table of values. So I'm going to go ahead and do that here. So you just go to the plus sign and put in a table and then type this in. So I want to make sure that I do not 1998, but -2 instead. I'm actually going to put in all my years first, and then I'll put in all the other ones. Okay, and then come back up, and now we'll put in all of our populations. This is probably as exciting as watching paint dry, so sorry about that. But hopefully you're typing them in right now as well, so that you can also look at it yourself. Okay, so we have that part typed in now, and you can see I'm going to go ahead and hide this line here because I don't really need that. There we go, that y equals 10 there. I'm going to go ahead and hide that piece as well. So here's the data is the red dots there, the red points, and you can kind of see how well they do line up, right, with the curve. And you might seem perfect at first, but if you keep zooming in, you'll see they are certainly not perfect, and they do deviate, eventually. The only one that is perfect is this one here, this year 2000, because that's the one that we based the model off of. So zooming back out here, now you'll see what happens as we're kind of traveling through time now, aren't we? We're going into the future and seeing what happens to this exponential growth model. So here's 500. This is the year 2500 over here. So you can see that the population is quite large. I'm going to keep going until I can actually see it within the screen here. So there it is, right? It was like 2,700 something, right? It was in the year 2,500. Like roughly right there. Yeah, so you can kind of see how quickly this exponential model grows, which might not be realistic, right? In certain situations. This is one of those situations where it's not the most realistic as you continue on going through time. So let's take a closer look at another model. So the model that we just looked at, the exponential growth model, has a constant k value, right? Like we found a k value based on 2 data points. And then we used that k value throughout the whole model. So this one shows a constant K value, a constant relative growth rate. And I apologize for piggybacking over here for one moment, but I remembered I wanted to mention that there is another way that you can calculate this K value. Let me just talk about that really quick, and then we'll pop back over here to another model. So I mentioned that there was another way to calculate K that you could see in other sources, and that is using the differential equation instead of the solution curve. So when we found K, we used basically this population model, didn't we? We used the solution to the differential equation as opposed to the differential equation itself. So you can use the differential equation itself to find the K value. The way to do that is you estimate the derivative at that point, or the growth rate at a particular point, and then the population at that particular point, and then you simply solve for K, right? We saw that before. K was the dp dt divided by P. So if you do that, like if I pop back over to the table here, probably the best way to calculate the derivative at 2000 would be the two nearby data points, right? So what you could do is find the average growth rate from 1999 to 2000, and then the growth rate from 2000 to 2001, and then average those growth rates. So I'll just do that in Desmos really quick to show you what that would look like if you're kind of curious as to how to calculate other values of K. So let's see, it would be 6.084 minus 6.008. Now we'd be dividing that whole thing by 1. I just want to make sure we're clear that I'm finding a slope between those two data points. So this means that, that the population increased by about 0.076 billion people between 1999 and 2000. So then we do the same thing for 2001 to 2000, dividing by 1, and then we would average these. So you can kind of see already what the average is. It's going to be 0.0755. So that's what our estimated dp/dt is 0.0755 dp/dt. Oopsie. dp/dt is about 0.0755, and then the p-value at that 0 was 6.084. So we would divide those to estimate a K value if we were going to be using this particular way of doing that. So it'd be 0.0755 divided by 6.084. And you can see it's pretty close to the one that we found before. So it comes out to be 0.01240,959, blah, blah, blah. We had 0.01225. So this produced a larger K value. Now, who's to say whether that's more accurate or less accurate? I suppose we could use this to see whether it is more accurate for the model, like in the year 2010. Let's just play around with that for one moment here. So if I do P of T, I don't really want to I'll do a lowercase p, how about that? Equals, and then 6.084 e to the, I called that lowercase c. So this is like the other model if we were to find the K value using this technique. So let's just see what it says for 2010. It has 6.887, so I'll just say 6.888 instead. And what we found before was 6.877. So let's see if that's more accurate. 6.877. So this way was more accurate. That is, finding the K value using kind of logarithms and using that population model instead. So I'll just write that over here for one moment. We found P of 10 to be about 6.888. And that's less accurate than the one that we did before. Okay, so again, these are models, right? There's no perfect way to model, but there are better ways of modeling. And so this is just another way that you can find a K value. It may or may not be as accurate. It probably just depends on the situation. It might be more accurate in another situation. So anyways, okay, so moving on to that exponential model in general, no matter how you find that K value is constant. It's assuming that your population is going to basically grow proportionally at the same rate the whole time. And that's not going to always be the case, right? So there's usually going to be some sort of carrying capacity to any sort of system, especially, the planet Earth. There's a carrying capacity to the planet Earth. So we might be able to kind of broaden this model a little bit better to make it more realistic, and that is what the logistic growth model does. So that's what we're going to take a look at now. What we'll actually see is that as the population gets larger, that relative growth rate should decrease since there wouldn't be enough resources to support so many people. So you might recall we looked at the logistic equation a few sections ago, and this is the differential equation, the logistic differential equation. dp dt is Kp times the quantity 1 minus P over M. So you might recall that M was the carrying capacity, and K is still the growth rate. It's just kind of more the growth rate based on the logistic model as opposed to the exponential growth model. So we have our table again here. Now, we're not going to dive that deep into the logistic model, but I wanted to at least show you this model so you could see how much more accurate it is than just the exponential growth model, especially to model population where there would be some sort of carrying capacity involved, which I think most would be the case. So if we take a look at the per capita growth rate or relative growth rate for the Earth each year in the table, so basically if you calculate that K value for each year, what you'll actually see, and you plot that compared to the population. Let me actually put some units, or I guess my labeling my axes here. So this vertical axis is the K value, the per capita growth rate or the relative growth rate, and the horizontal axis is the population. Okay, so I'll put that here and here as well. And I guess it does have P right there, K. P. Okay, so basically what we're doing here is we're graphing all of those different K values, those per capita growth rates, as a function of the population. So you can see that as the population increases, the relative growth rate decreases. And not only does it decrease, but it seems to decrease at a relatively constant rate, doesn't it? So we can actually put a linear model to this particular relationship and find an equation that can model the per capita growth rate as a function of the population. Let me explain this kind of path here for a moment before we jump into that next part, because this threw me off when I first saw it, so I just wanted to explain what's going on with these graphs here. So you can see, notice that these two graphs start at a population of 6.0, just since that's like roughly, where most of our populations are. And then when we jump over to this last one, which is where we really get that equation from down here, you can see it then extends over to 0. So if you were like, wait, this is like at 0.012, and then now this is at like 0.025, what's going on there? It's just kind of a shift in our axes. This one shows a bit more of the data, so that's all that's happening there. So you can see that this equation, if you were to find the slope of the line, right, and the y-intercept of the line, you would get about K equals 0.025 minus 0.002p. So again, that shows the relationship between that relative growth rate and the population. As population increases, we will see that relative growth rate decrease as the population approaches its carrying capacity. So with that in mind, with this relationship between K and P in mind, we can kind of modify that exponential growth equation and take it from being dp dt equals Kp, right, where we just have this constant relative growth rate, to now having a variable relative growth rate that is based on, actual data that we found for the Earth's population. So when we do that, we're basically just replacing this K, right, with this relationship that we found, 0.025 minus 0.002p. And what we get, I think I'll actually leave that there. Maybe. There we go. I'm putting that in there. We get dp dt is P times that quantity, 0.025 minus 0.002p. Hey, that is a logistic equation. And this is then the logistic equation that models the growth of the population of the Earth. Okay, so what we're going to do, we're going to play around with this model a bit. And again, we're not going to dive that deep into the logistic model, but I really felt like it was worth looking at because, right, I think that the exponential growth model, it's lacking a bit, isn't it? It's like we kind of want more. We leave wanting more. The logistic one you'll see ends up being a better representation of the Earth's population. So here's what we're going to do. We have had some exposure, right, already to the logistic equation. Again, we know that m is the carrying capacity. And so what we're going to do is we're just going to rewrite this differential equation so that it's in that form that we were comfortable with before. So here was the one that we found based on the model, the data rather, from the Earth's population. So it was dp dt equals p times the quantity 0.025 minus 0.002 p. Okay, and oops, I don't need a screenshot. Okay, so we're going to write it in this form. So I'm going to point out one thing here with this particular form. There's a 1 here. That's kind of an important piece to that particular representation of that model. So what we're going to do in order to get that 1 there, I'm going to just give myself a little space to work here. We're going to go ahead and factor out this 0.025. I'm going to do that in a different color. So 0.025, and that way we're essentially dividing all of these by 0.025. And that will give us that 1 that we need in that model. Anytime I have division, if the parentheses aren't elongated, it bothers my eyes. So, okay, there, and then we'll center that a little bit. Okay, so we'd end up having 0.025p, 1 minus, now we want this part to be p divided by m, okay? So I'll actually just highlight the m part. We already have a p part. So p divided by m. So what I want to do is make this a p, and then I want basically all of these constants to go into the denominator. So to do that, we're going to reciprocate. So right now it's 0.002 divided by 0.025, but I want that to be in the denominator, so we're going to write that as the reciprocal. So 0.025 divided by 0.002. And I'll spare putting this into Desmos, feel free to, but it simplifies quite nicely. This 0.025 divided by 0.002 simplifies to 12.5. So now this is written in that kind of prior logistic model that we've looked at before. And so now what we can see is that this is the carrying capacity. So m equals 12.5. And so that's billion, right? Billions of people. Billions of people is the, I'll say estimated carrying capacity of Earth. Isn't that so cool? 12.5 billion people. Okay, that's kind of what we can expect. Let's play around with this model a little bit more here. So we're going to go ahead and put this into GeoGebra, right? Because we've kind of seen GeoGebra tends to do differential equations a little bit better. You can solve this differential equation by hand, okay, using the separation of variables technique. It's a little bit labor intensive. It involves a partial fraction decomposition, all manageable, and maybe you'll do it in the future. For right now, we're just going to go ahead and use GeoGebra to do it. But if you're really interested in how to do that by hand, just ask and I'll lead you in the right direction. Okay, so here we go. We're going to pop over here to GeoGebra now. Oops, there it is. Okay, I have GeoGebra. All right. So what are we going to do here? We're going to look at the slope field of this differential equation, the logistic one, and you can write it in either form. I think I'll go ahead and actually use this new form that we have here. And then we're going to actually solve the initial value problem and visualize the population of the Earth over, an extended period of time. Okay, so let me scroll down so I have that there. Okay, so here we go. So remember to do this, we do slope field. And notice that we have to type it in as a function of x or y. So x would be the independent variable, which in this case is t. I don't see, there's no t's, right, in our equation here. And then y is the dependent variable. So that would be p, right, the output variable. So just keep that in mind when we type this in, I have to use y instead of p. 0.025y. 1 minus y divided by 12.5. Now I'm actually going to go ahead and copy this because I'm going to use it later. But I'll hit enter and we'll take a look at the slope field. Now we probably want to adjust our axes here so we can see a little better. I'll just start by zooming out. I definitely want to make sure that I can see 12.5. and 6, right? So 6 is our initial population, 6 billion. 12.5 was our carrying capacity. So we definitely want to be able to see kind of that range there. And we probably want to zoom out quite a bit in the years, right? Years after 2000 to kind of see what's going on with our slope field here. So the initial population was, right, about 6. So you can see what happens to the population. It increases. I'm following the slopes. Increase, increase. And you could, I hope you can see I think you can see my mouse right now. If not, I'll go ahead and just use the pen here. So this isn't part of the question, but just, you know, if I wanted to freestyle this, I'd start here at 6 and then follow the slopes. Increasing, increasing, increasing. And then it kind of seems like it's leveling out, doesn't it? Around 12.5. Keep going. I may have gone up a little bit too high. These can be kind of tricky to do. Okay, so we're gonna let GeoGebra do this for us because it does it much more accurately, at least compared to what I do. So we'll do solve ODE, and we'll have a specific point on F. Now this is where my copy paste comes in handy. I copied that earlier, so I'm going ahead and just pasting that in there. And then now I have the coordinate point. Let me extend that out a little bit. Coordinate point on F, which is 6.084. And you can see mine is not very good, so we're just going to go ahead and delete all of that. Pretend it doesn't exist. Yeah, it can be really hard to follow those slopes correctly. But you know, you get the general idea as far as like it increasing, slowly increasing. Well, it increases quickly at first and then more slowly as we go. And I will go ahead and actually, let's travel through time again. And you can see, right, you can really see that kind of approaching that particular carrying capacity. Okay. Okay, let's pop back over to our notes here and see what we want to do with this. Okay, so we visualized that. We solved that initial value problem. It gave us an algebraic formula as well for the solution. Did you notice that? F of x here. So I'm just going to go ahead and keep this as an F. If you wanted to, you could rename this a P. It already called it F of x. I'm okay with that. So what we're going to do now is we're going to answer the same questions that we did before with the exponential growth model, but now with the logistic model, and kind of compare and see how those see how it works. So let's try to predict the population in the year 2010. So that would be P of 10, right? I'll go here. P of 10 is about, and we'll go ahead and put F of 10 in here because that's what GeoGebra called it, 6.863. 6.863. So let's compare that to the data. Keep that number locked in your mind. 6.863. Come back here. 6.863 compared to 6.831. Okay, so that's pretty close, isn't it? Especially if we compare that with the exponential growth model. So 6.863 was the logistic, and it was 6.877. So the exponential growth model kind of overestimated the population of the Earth in the year 2010. Kind of makes sense that it would be an overestimate, doesn't it? Because it, you know, it has that relative growth rate being constant, and so you're just going to kind of keep having that continuous rate of growth, which is not what it really should be, right? So definitely, I would say more accurate than the exponential growth model. I'll just put EGM, exponential growth model. Feel free to write it out in your notes if you're worried you won't know what that means. So this is the logistic growth model that we found, and that looks more accurate. Okay, let's look at part 2 here. Part 2 says, when does the logistic model predict the population will reach 10 billion? And we're just going to go ahead and use GeoGebra to solve this. So go ahead and put in y equals 10. So very similar to what we did in Desmos earlier, right? When we put in 10, and then we just looked for the intersection point, kind of those two. So we did that earlier. Ended up being about 40 years later, so 2040. But with the logistic model and GeoGebra, we'll do intersect, select. It doesn't matter what order you do this in, just make sure you select both curves at some point. And we get about 57.577. So P of t equals 10 when t is about 57.577. Is that what it was? 57.577. So that's years, right? So about the year 2057 to 2058, somewhere around there. That sounds a bit more accurate than the other exponential growth model, which predicted in the year 2040, roughly in the year 2040 or 2041, that the population would reach 10 billion. It would be longer than that. It would take longer than that. Okay, let's see. For part 3, what does the logistic model predict for the population in the year 2500? Okay, so that would be P of 500. Okay, so again, that's F in this one, F of 500. Okay, I get 12.49995. I feel pretty confident rounding that to 12.5 billion. So roughly, carrying capacity. And that sounds pretty accurate. This does seem reasonable. Does seem reasonable. All right, and then in part 4 here, we'll use the logistic model to estimate the population of the Earth in 1975, and we'll compare that again to what we found in the exponential growth model. So F of negative 25, 4.208 roughly, 4.208 billion, and you'll recall that we actually found it to be I don't recall exactly what it was. 4.479 was what the exponential model predicted. It was actually 4.063. 4.063. The exponential growth model found it to be, sorry for all the scrolling, 4.479. 4.479. So definitely more accurate. Okay, so hopefully you're seeing so far that the logistic growth model for population tends to be a lot more accurate than just assuming, that exponential growth model and having exponential growth at a constant rate, essentially. Okay, so let's go ahead and graph that data along with the solution curve to the exponential model, and then also the solution curve to the logistic model. I'm going to actually go ahead and write the algebraic formula that GeoGebra gave right here. So maybe I'll even use a subscript here. PL, I'm using L for logistic, was, I'll do a little split screen. Split screen is definitely my friend here. All right, so it was 38025 divided by 3208 e to the negative x over 40. I'm going to end up typing this into GeoGebra just because that's where I happen to have all the data and all that typed in already. So you could certainly do, GeoGebra instead of Desmos. Okay, so I'm going to go ahead and I'm going to get rid of this and that and some of these other things here. Don't really need any of that. And I'm going to go ahead and label this with a subscript E. And to do a subscript, you can do Shift, basically like an underscore, or you can use the keyboard here. Okay, so this is the exponential model, and then I'll go ahead and do the E here as well, just so that those line up. I do it there too. Okay, so these are all my exponential model ones. So now I'm going to do the logistic model. And this is going to be 38025, 3208 e to the negative x over 40 plus 3042. Oh, it's mad at me. Oh, because I put an x in there instead of a t. There we go. Okay, so let's go ahead and bring all that together here. So what we have is, and I'm going to get rid of my 10 there so that we have our 3 things to look at here. We have the data, which is kind of these red points here, and then we have the exponential growth model in blue, and then we have the logistic growth model here in green. So you can kind of see like that it definitely seems like the logistic growth model is more realistic to the actual population of Earth. It is nice to be able to see all of those in one. Now, we're going to also answer this last question, which is based on the exponential model, in what year would the Earth's population reach the carrying capacity that we saw in the logistic model? And we're just going to use GeoGebra or Desmos to do this. So we know that the logistic model had a carrying capacity of 12.5. So we're basically trying to figure out when does the exponential model end up predicting that the population will reach 12.5. And it has in, so 58.771. Okay, let me put that here. What we're really solving is P of t equals 12.5, and that seems to happen, let me put the exponential here just so that we're clear that I'm not talking about the logistic model, I'm talking about the exponential model, when t is about 58.771. So about the year 2058 to 2059. Okay, but again, that's with the exponential growth model, isn't it? So we've already seen that the exponential growth model doesn't seem as realistic as the logistic model. So here is kind of just a quick summary of the logistic population model, and feel free to just use this if you do have any, homework questions in there. You don't have to solve this by hand. But this is the logistic model for the differential equation, and this is its solution to the initial value problem if the initial population is p sub 0. So we end up getting p of t is m over 1 plus a. A is this constant. It's just a little bit nicer to write it as an a, e to the negative kt. Well, I hope you enjoyed exploring population models a little bit more, and we'll keep working with finding these, or like basically looking at applications of exponential growth and decay.